Good morning. Our next speaker is Alper Nebi Yasak. He is a hacker from Turkey, and he likes to play with many things and tries to make things right. And do you know about Chromebook? It has a Chrome OS installed on it, but its boot procedure is a little bit different and from the other computers, and it is difficult to install another operating system on it. And it is difficult to install Debian as well. Have you ever thought about installing Debian on it? Have you ever tried it? Alper has not only tried it successfully, but he has also improved the Debian installer so that other people like me and you can install Debian easily on Google Chromebook. So for more details, let's listen to the talk of Alper.
Thank you. I'm a Debian user from Turkey. I've been mostly fixing issues on my devices running Debian. That's my involvement in Debian. I have an ARM64 Chromebook and I've been working on it, and with that I helped enable graphical installer for ARM64. I'm a bit good at software stuff, if I should brag, but not so much with social things. So I try to do things alone, unfortunately. I'm interested in hardware freedom, which led me to these devices, Chromebooks. What are Chromebooks? Chromebooks are actually... okay. No. My slides are acting up. No, stop. What is a Chromebook? Chromebooks are Google devices that are, yeah, okay. It's not going to do that. Let me read from here. Chromebooks are Google devices, laptops, detachables, tablets. They run Chrome OS, which has been basically Google Chrome as an operating system designed to run Chrome OS as fast and as securely as possible. They are usually low-end devices that connect to the internet and do everything on the internet through Google Chrome. More powerful ones also exist recently, but I mean, the things in Chrome OS is getting improved with Android app supports and Linux container supports. They are mostly popular in the US education sector. And how are they different? They are different in that they cannot put anything other than Chrome OS by default. Yeah, I don't know why is it switching like that. Sorry about this. They are very much locked down. They are very wrong slide, but they are very much locked down. Their root file system is read-only and verified through hashes at boot. There's basically no way to run unapproved code in the context of a Chrome OS. It pushes users toward Google services because the hardware is less powerful. For example, it has 32 gigabytes of eMMC, which means you should use Google Drive and etc. Yeah. How do they? Why are they interesting? Why are they interesting? Google Chrome is actually Chrome OS is actually a Linux distro based on Gentoo. The firmware on these devices is based on coreboot with a custom payload called Depthcharge. That is by Google. But almost everything is free and open source software with an open core model like Chromium and Chrome. They are available on chromium.googlesource.com, and even LibreBoot used to support an ARM Chromebook, and that's how I actually got into this stuff. I was looking for a free software computer. I went into LibreBoot hardware things, and so the most modern thing it's supported is this one ARM Chromebook. Then a few years later, there's another ARM Chromebook, which is this one, Samsung Chromebook Plus, which looked like the successor to that device. And I said this would be the next one, basically, that would be free software compatible. And to get Debian to boot on it, we must first investigate how does Chromebooks boot Chrome OS. They don't use the conventional BIOS and UEFI stuff that we know about. They use verified boot flow designed by Google. There's the computer starts with the read-only portion of the firmware. Then that read-only portion verifies signatures on an updatable part of the firmware and launches it. That verifies something called the Chrome OS kernel partition on disk and launches Linux. From that, Linux reads the disk and verifies the file system hashes and stuff like that. On more recent Chromebooks, there's a Google security chip which acts as a root of trust and even verifies that read-only firmware, because that read-only firmware is actually upgradable, but it needs some disassembly on the device. There are, as I said, signature checks everywhere, so basically no way to inject anything else if you don't get permission from Google. There's also a recovery mode, which in case things go wrong, you just press a key combination and read-only firmware launches special recovery partition things that you can plug in from the USB. And the important thing with the recovery mode is it lets us enable something called developer mode, and this developer mode wipes out the Chromebook first, so that you do not compromise anything that is existing on the device. It shows a warning on every boot, so an ordinary user would be easily going back to the verified boot mode. The benefits developer mode gives us in Chrome OS is a terminal, the ability to mount file system as read-write. It allows us to use non-Google signed images for verified boot. That is what I have been trying to do. It lets us boot from micro SD cards, USB drives instead of the internal eMMC. It also gives us access to two other functions called legacy boot and its successor alternative firmware. Legacy boot is a mechanism that lets Google's Depthcharge firmware chain load another coreboot payload. On x86 machines, there is sometimes a CBIOS deployed by stock, but it might have defects. There are third-party providers like Mr. Chromebooks, which provide better versions, so people download his versions and update the legacy boot firmware on their computer. With developer mode, they launch the computer and get the warning screen, and on the warning screen, if you press certain key combinations, you can launch the legacy boot firmware. Then it acts like a old BIOS computer. This was believed to be unavailable for ARM, but there's just no stock payload. So when you press the key, it beeps and goes back to the beginning. Does nothing. I said there's a Chrome OS kernel partition that the firmware reads and launches. What is that? What goes into that? It's a combination of a vBlock header and the data it signs. The vBlock header has some key blocks and the signatures of the signed data it signs and some flags for telling the firmware what are you allowed to use this image for. I'm calling it a Depthcharge image because Depthcharge and image. I don't know if there's an official term for the file format. The outer format is the same, but the inner format depends on the board and architecture. It is, on ARM computers, it is flattened image tree from U-boot. on x86, they call it something like Z image, but that might not be the same Z image you get when you compile the kernel. I don't know. There's also mentions of multi-boot and zircon boot image, the latter of which is Google's Fuchsia kernel packaged in some format. I haven't looked into these much. The features and checks that the firmware does to the Depthcharge image depends on the board and architecture. For example, on older ARM computers, you cannot compress the kernel in the flattened image tree, but on newer ARM64 ones you can. Things like that. There's also a size limit on the signed data because it is copied to a fixed buffer in memory. That depends on the age of the board, from 8 megabytes to 512. On the one I have, it was 32 megabytes. So now that we've went through how to boot Chrome OS, how can we make it boot Debian? And step 0 is to actually get a working kernel from Debian. And the parts of it usually are to get mainline Linux support, which is kind of easier because Google's already usually doing it, and at least publishing the source code as open source. And then we identify some necessary kernel modules for the drivers of the hardware that we need to support, and we have to enable these in the Debian kernel package, the configs for these. And we need to add the modules to FOSS tools, so when the Debian operating system updates its parts, these will be available during boot for the hardware to work. And we have to add these to the installer udebs lists so that they will be available to the installer, and the installer will even be able to work on the hardware. After this, the first two parts were already done for my device, and I just helped do the others. And after that, we need to enable a developer mode and partition a disk to install Debian on, and it needs a Chrome OS kernel partition with the root file system and everything in Debian. After that, we debootstrap an ARM64 installation, which is a normal step that you would do. Then we make the Depthcharge image for that installation. We write it to the kernel partition. Then we need to set some GPT flags to let the firmware know that this is something it wants to boot. So creating the kernel partition is easy. GNOME Disks utility supports it. GNU Parted didn't used to support it, but I added the Chrome OS kernel flag, and now you can do it from gparted, for example. After creating the partition, we make a Depthcharge image. We need the kernel initramfs device tree. We need to know the parts we need to put into the kernel command line, and we need to key files from the Google's verified boot utilities. These are packaged in Debian as vboot utils or vboot kernel utils, and the last one, cgpt tool, that's also packaged. Since there's a size limit and the kernel and initramfs doesn't fit, I compressed the kernel to LZ4, and the Google's vboot utilities have some weird input files that are necessary. It takes the kernel command line as a file, so we need to create a file for that. And it also needs a bootloader file that is not empty, so we have to create a non-empty file. Doesn't matter how much size it is. Then we create a flattened image tree with the mk image utility from uboot using the previous files. Then we use this flattened image tree to sign the things the way Google's firmware wants, with VButil kernel program, and another line to test that it is actually under the size limit for my Chromebook. The final step is to actually write this file to the kernel partition and set the priority, tries, and successful flags. The firmware compares the different kernel partitions based on how high priority they are. More priority is chosen to be booted. It decreases the tries partition so that it knows when to stop trying to boot that partition, that it definitely doesn't work. And successful means it has booted successfully, and we can try to boot it as many times as possible. It doesn't matter the tries thing. So we do all these, reboot, and things work. But we need to do this on every kernel upgrade, every interface change, every kernel command line change. And this might be very frequent if you are using Debian testing or even unstable. And it only works for a single Chromebook because I only put the my Chromebook's device tree file on the thing. So I say there must be a better way. Grub can update itself. For U-boot devices, there's Flash kernel, which can update itself. And Debian Installer can set these things up. And it can do the partitioning, for example, for EFI devices that need an EFI system partition. And it should be that easy for Chromebooks as well. I said there is Flash kernel for U-boot devices. Can't we integrate to that? We can. It supports most of the things. I tried to actually implement it. There are a few features we need. It doesn't yet support x86 devices, and my attempt didn't get reviewed. The maintainer didn't have the time. And since these devices can support U-boot, if we use Flash kernel for it, for the Depthcharge firmware, it will be harder to use it for U-boot and to support U-boot for the devices. So I made a tool inspired by Flash kernel, a single piece of software to make the board bootable. I have a long list of configuration files to enumerate all the things that every board supports. It checks these to determine what it has to do and have a single command that you need to call that does everything for you, tries to do the right thing. It's just enough that we hook it into the kernel and interface changes, and everything will be great. So, in the most basic sense, I call it Depthcharge control, and the suite of tools I call Depthcharge tools, simple naming. You just run Depthcharge control build, and it detects your board and collects the files necessary for the latest version of the kernel you installed and creates the Depthcharge image. I also added a check subcommand which tries to check if the image would be bootable on your device. And for example, it detects size limit constraints and wrong formats and wrong device trees and things like that. I would like it to be exhaustive, but it's not complete yet. Other than that, there's a Depthcharge control write, which takes in an image and writes it to a correct Chrome OS kernel partition. If you don't give it an image, it builds one on its own and writes it to the correct partition, which is actually the command we need to call. Other than that, we need to remove older kernels because their modules are gone, drivers are gone. If we try to boot older kernels, when they are not installed, they are not going to work. And there's a remove subcommand for that. And after making these, how do we integrate into the Debian updates mechanisms is there's actually standards standard ways to do this. In the kernel team handbook, there's an excerpt from that. There's Edge init post update and Edge kernel post inst and post rm. Basically, it gives you some parameters of kernel version in init files, and I run Depthcharge write the version, and for post install similar Depthcharge write version, and post remove is Depthcharge control remove force version and things like that. The tools I made are very configurable, if I say so. Yeah, not to brag, but okay. Then what happens on a bad upgrade? Since we have only one kernel partition and we overwrote it with a bad image, we have no way of booting anything on the device anymore. We have to boot another OS from another disk and rebuild and rewrite a correct image for the thing, for the Chromebook. Chrome OS can do rollbacks, and I thought I should do it as well. How does Chrome OS do it? They have two A-B partitions, and they boot from A, upgrade B, mark B as bootable, reboot to B, and if it's successful, mark B as always bootable. If it's not successful, on the next boot, it automatically disables the thing and goes back to A. But the OS needs to know which partition was chosen by the firmware, and the Depthcharge firmware accomplishes this with one thing, the kernel command line. It prepares cross-secure to tell the OS that it is using Depthcharge firmware, and it replaces a %u pattern with the partition UUID of the chosen partition. And Chrome OS uses the UUID kernel command line while building the Depthcharge image, and the firmware fills it in, and the OS has access to it and marks that partition as successful. How we do it in, we could also do something like this in EFI systems with EFI variables and boot counts, things like that. There is systemd boot that does this, and I'm inspired a bit with that, especially its bootctl command, which is an similar to what I want to do. It would find and list entries, set default entries, set one-shot boots, init services to mark successful boots, things like that. So I added some things to my Depthcharge control software, which is Bless, which reads the kernel partition part UUID the same way Chrome OS does from the UUID kernel command line. I also made the build subcommand inject this thing into the kernel command line automatically, so it will be available. There's also a one-shot argument that you can say, oh, let's boot this partition on the next boot, but only on the next boot. So we would fall back to the current one if there's any problem with it. I added a target subcommand that chooses the worst partition that would be the least priority unsuccessful partition to overwrite, so that we can choose the best partition to write a new image to. For the init service, there's a systemd bless boot generator that creates a init service something like this for systemd bless boot, and I just copied from that. What's important here is the requires boot complete target and the wanted by basic target, which makes my command Depthcharge control bless run on successful boots. So after these, we have an installed system that can continue to run Debian as long as it can automatically with no problems at all. But we did the installation manually, and that's a problem I don't like. So how do we integrate into Debian Installer? What we need is to do Chrome OS kernel partitioning, and we need to set up the bootloader after the installer, the Depthcharge control write command, and we also need custom images that can boot on Chromebooks with the Chrome OS kernel partition. For partitioning, the Debian installer's partitioner is Partman, which is a powerful modular framework based on hooks. It has many components that add every piece of functionality into it, and the underlying implementation is GNU-parted, which is also why I had to add the Chrome OS kernel to the parted software to get this working. The most complete explanation is that I found is at this website, Partition Management for the Debian Installer. Here's an excerpt from that. After the talk, maybe if you get the slides, you can read through it. There is too many hooks for stuff, for synchronizing state from and to the disk, and to do checks and validations after partitioning, and to display text, and to display menus. But it's better and easier to copy from existing projects. There was a Partman prep which almost did the exact same thing that I want with another type of partition. So most of it I copied from there and made something called Partman cross, which enables manual creation of these partitions and warns you if you have booted with verified boot but not added a Chrome OS kernel partition, which would make your system not bootable with the boot method you use. How does it look? In Debian Installer, you get to the partitioning step and choose manual partitioning, then choose the disk, create a new partition, and enter the size. I also adjusted the names and labels, and you choose the use as thing to that would let you use file systems and partition types, and it gives you this list of things which now has the Chrome OS kernel partition next to the UEFI system partition. Then after that, you just have the name and the Chrome OS kernel partition, because nothing else really makes sense in this menu. You are done setting up the partition, and I added another partition, which both of which now show as CROS cross partitions, short for Chromium OS. Then, yeah, I added two partitions, then continued the rest of the installation, which works fine. But if you don't add these partitions, my components would warn you for because you have no usable Chrome OS kernel partition, and you should go back and resume partitioning. If you add the partitions, it works all fine. So that's one thing done, the partitioning. The second is a post-install call of Depthcharge control write. For that, we need to add a Debian installer step, and what actually they are is UDEB packages. Every step is a UDEB package. While creating the Debian installer images, the build system downloads the UDEB files from the archive and unpacks them in an unconfigured state, then collects everything into that ISO file, CPIO image, which is the interface which goes into the ISO file and things like that. Running a step starts configuring the package, which runs the post-install maintainer script, which installs the package, and the package metadata controls the order and appearance in the main menu and dependency chains and whatnot. There's another great guide for this in the Debian Installer DI Debian.org documentation. I'll skip some of the technical details here for time, but you can have dependency between steps, you can have order, you can have multiple steps doing the same thing, skipping some of these. You have Debian templates for questions, errors, info messages, and runtime configuration values that interact with other files. Debian post install is what is executed when you run the step. You use the DebConf configuration management system to interact with the Debian installer and display things, whatever you want. And there's Debian is installable, which determines whether the step is shown in the main menu or not based on its exit status. So we can, for example, make the partition step invisible on certain kinds of systems. So with these, I made a Depthcharge tools installer udeb package, which is a post-install step that runs the command I've been doing in the target. If it would be a shame if it failed when the interface is too big, so it offers to make it smaller by reconfiguring the interface tools configuration. If at the maximum compression and using only dependent modules, if it cannot be smaller, any possibly smaller, it just has to give an error, too bad. I can make it only visible when using verified boot by checking the cross-secure command line parameter, and it provides bootable system, and if it is successfully executed, grub and flash kernel steps automatically are skipped because they also provide the same package, and there's no need to run multiple things. So here's how it looks in the main menu. The main menu isn't usually visible in the Debian installer. You can press escape a few times to go back to it, or set DebConf priority to low to see it. But these are the steps that are sequentially executed in a normal operation of the installer. We have make this Chrome OS board bootable just before the install, grub and continue without bootloader, which are skipped if my step is successful. Then after that, finish the installation. These images are from a QEMU virtual machine, so that's why grub bootloader is available. It's an EFI system, actually. I'm simulating the Chrome OS things in the virtual machine. That's hard to debug and stuff. So when the step starts executing, it should install the Depthcharge control tools from the Debian archive, but they are not in the Debian archive. So I have a previous step, install custom packages target, that I'm injecting the package into the install system. Then I'm doing this Chrome OS board bootable step. After that, it regenerates the interface if in case the configuration changes. After that, we call Depthcharge control write in the target, and it will build and try to write the image in using the already installed systems things. If it fails, it says it could not generate a small enough boot image. Do you want to reconfigure interface policies? At this point, saying no is a failure of the installation. So you just go with yes. Then there's 2 DebConf questions, which is the first of which is already in Debian Installer at a low priority, asked in based installer, I think, which asks you if you want to include all available drivers or only include drivers needed for the system. You can configure this to make the interface smaller, or you can change the compression in the interface tools configuration. That would also make the interface smaller, because, well, that's the only thing we can make smaller at this stage. The compression options are gzip and LZO, LZMA, LZ4, and the highest compression is XZ usually. And if you do that, say yes, then the installation completes successfully, and rebooting to Debian actually works fine. And since the Debian installer already installs the Chrome OS bootloader management things that I put into it, it will continue to work after kernel upgrades and things like that. The final piece of the puzzle is the custom images for Chromebooks. We need custom images that have the Chrome OS kernel partition. But this is practically the same as what we are already doing with ARM netboot SD card images. They have a common installer partition and a per board firmware part. We can just use the existing mechanism to add a Chrome OS kernel partition for a board or a general one as a firmware part, and use the existing systems. But I haven't done that yet because there's a problem with this entire thing. Bad news. The ARM64 netboot interface doesn't fit into the size limit of my board anymore, even with XZ maximum highest compressions of XZ, because it's full of boards that it won't use Ethernet and things like that. I mean, I can get it to work, but that wouldn't be appropriate for the Debian installer build system. It's even worse for 32-bit ARM boards because the limit is lower. And another problem is there's no known way to use any interface with Depthcharge on x86 Chromebooks. It's a shame, but that's the state of things right now. So was this all for nothing? Not actually. The newer Chromebooks have a 512 megabyte limit, which is generous, and Debian installer completely fits in it, no problem. And if you look at the source code of Depthcharge and vboot kernel utils, we see references to a RAM disk address, which means which is set to 0 to disable it, which means it is possible to set it to something else to enable it, probably. So it implies it can support interface. And the holy grail is that we don't have to boot Debian installer itself with verified boot. We just need to boot something that boots Debian installer. It can theoretically, it can be, for example, a Linux kernel that KXX into Debian installer, or something like shim, what shim is doing with EFI, a secure boot, or even maybe we can get grub to working. But there's one thing I know that works: U-boot. U-boot works as a Chrome OS kernel in 32-bit ARM Chromebooks, which is fine. There's guides on it, but if you follow those guides, it normally doesn't work with ARM64 because there are additional checks that the Depthcharge firmware does that no one previously adapted U-boot to work on it. No one, but reading through the source code gives you these what's necessary. One part of it is an ARM64 Linux kernel image header magic value, that needs to be built into the U-boot binary. And another is position independence, which is due to how the Depthcharge firmware locates the moves the thing it loads to an indeterminate place. These are both available as config options in U-boot build system, and when you enable it, things work on ARM64 devices just fine. But U-boot needs to support the board you are building for. That's the primary issue. But we can build U-boot as a Chrome OS kernel in the upstream build system. I'm actually working on trying to integrate it there. And when we do that, we can deploy these Chrome OS kernel partitions inside, for example, U-boot Rockchip binary packages for this board. And then Debian Installer can use those ones to build custom images. Other than this, we can actually completely replace the firmware. Coreboot is usually already upstream by Google, but it uses Depthcharge still. We need a different payload, which, for example, on our x86 devices, third-party providers use Tianocore EDK2. On ARM devices, we can use U-boot for this, and we can port drivers from Depthcharge to U-boot because they are similar in architecture. And after we do that, U-boot can also work standalone as well as the entire platform firmware. The good thing about replacing the entire thing is it fixes the Chrome OS bootloader issue permanently. You are no longer restricted to the Google's verified boot flow. But it needs per board work by many developers. It's also more work for the user because the flash chip is write protected. The board needs to be disassembled, sometimes almost entirely, to actually unprotect the protected parts. And if you are not doing it very well, you can brick the device, write wrong firmware, and the device becomes inoperable. And you also can't boot Chrome OS because none of the other payloads would support Chrome OS yet. Maybe U-boot will in the future, I don't know. Third option is the legacy boot mechanism. If we make coreboot if we can make U-boot into a coreboot payload, we can put it in the legacy boot partition in the BIOS flash chip, with which we can use the stock firmware and the Control-L key combination to boot into U-boot, which can then boot into Debian Installer and make it work like almost like a normal UEFI ARM64 computer. That would need almost no changes to Debian Installer at all. It seems like the best option, and we can still use Chrome OS with the other boot ways because we keep the stock firmware. If this thing is done, maybe Google can deploy it to Chrome OS boards in the future, but I don't think they will do it for already released boards. Once you have a payload built for the legacy boot thing, it's not that hard for the user to download it and write to the flash partition. It's just download and run this one command, which really has no chance of damaging the read-only firmware, and therefore the device will keep working, less risk of damage. Yeah. In summary, to solve Chrome OS things in Debian and Debian Installer, we need the kernel, interface, and installer support for the hardware with the kernel modules and putting things in the right place and config options enabled. Then we need Debian Installer images for Chromebooks with the Chrome OS kernel partition, and which will enable us to boot into Debian images with Debian Installer with Chrome OS verified boot flows. We need the partitioner changes and a post-installer step in Debian Installer to actually set up the system that will be able to boot Debian. And after we have installed, we need kernel and initramfs hooks for updates that will keep the bootloader parts in sync with the updated kernel and initramfs files. We need an init service for the seamless AB upgrade supports to make the system more resilient. And we can actually use U-boot as a Chrome OS kernel to make things really easy, which I think solves the problem for good. As I said, I omitted the title page, but the name of the talk was how can I use Debian on my Chromebooks for good? And well, this is the for good part of solving the problem for every Chromebook. That's what the title was intended to be. So, yeah, that's the end of the talk. I hope I haven't bored you that much. Thank you for listening.
Thank you, Alper. Great talk and such a wonderful project. Do you have any questions?
First of all, I'd like to express gratitude for excellent work you've done and also a fantastic presentation. Well done. So, yeah, then also extending to express if you need testers, I have 2 legacy Chromebooks. I'd happily be at your service to do testing as well if you need hardware. And then my question is there any virtual machine support for doing test development so that we can use something like QEMU emulating a Chromebook so that we don't have to use the hardware all the time?
Great question. What I do is to add some DebConf templates to the parts of the Debian installer that I modify so that I can say, for example, to Partman Cross to pretend that this is a Chrome OS device and give the warning that you would give if you do not see a Chrome OS kernel partition. That just checks the cross-secure kernel parameter, and I can, for example, put that into the kernel command line while booting from grub. With the Depthcharge tools installer, I can say, pretend that you are this board named Kevin, and it will try to build the image for that specific Chrome OS board. And for example, I can run through the entire installation in QEMU VM. Then I can attach a USB disk to a QEMU VM. I can run through the installer, pretending that this is the Kevin board that I have. Then, after the installation is done, remove the USB and boot from it on this device, and it just works. For hardware, let's talk after, if you have time.
Yeah, thank you also from my side regarding a very interesting presentation and the hard work you've done on that. I can feel like I'm working on embedded devices as well. One question or one remark regarding your plan to move to U-boot as a coreboot payload. Are you considering then to use U-boot as a UEFI provider and simplify basically all the steps afterwards? Is this an option for you?
I mean, it looks like it will work that way. I mean, that seems to be the easiest option to keep things up to date, especially on the limited size boards like mine. For example, this one has a 32 megabyte limit, which is already pushing the bounds with the kernel and initramfs of a Debian installer, and I have to configure the initramfs tools to use the say only build the only build the kernel modules that are that these ports use into the interface so that it's smaller, things like that. I don't know what exactly things are going to, what way things will going to go. So can't form a sentence, but I mean, on this board that I got, I made U-boot actually work bare metal, and U-boot is getting slowly to the point where it can support UEFI. So maybe I will continue to use it that way. I mean, I have been using it that way for a while, but for this talk I switched back to the stock firmware and kept testing a few things. These are just the Chrome OS kernel and full firmware replacement and legacy boot. These are the options we have in addition to the verified boot flow. And I just wanted to enumerate them for more information. And I hope that answers your question.
Unfortunately, we have passed the time limit, so we have to close this presentation. But if you have any questions, Alper is here, and you can continue to ask him more questions. A great applause for Alper.